สรุปนี้เลคเชอร์อะไรนะ Okay, so we continue on perturbation theory. So today we're going to look at harmonic perturbation. Okay. So, well, we look at, we are actually interested for the periodic external field. So that you put electric field in this form. So that actually in this direction, okay? So, and we also consider in the case that your omega, I mean the external frequency that you put into your system, approximately more or less the same with this one, which is the energy difference between the different energy level in your system. And of course, if you set this condition, you know that it's going to give you resonance. Yeah, in this particular case. If not, then you are not going to get. Well, you know what is the resonance, right? You learn from the basic classical mechanics, right? Right. If your system have its own frequency, and if you disturb it with the frequency which is actually very close to this its own frequency, then you will get that kind of resonance, that kind of thing. Okay, so we know, right? What you are doing over there? Get out. Find something to do. Make yourself to be useful. Okay, so suppose that we have a potential in this form, and so we're going to use this notation. Right, then, so okay. So you have to keep in mind that actually this had to be swapped, because this is you get dagger here, and then you get the complex conjugate. So with this, you can think this is a perturbative term, right? then you can write out the first order of the C. This one, which is actually, we learned how to derive it from the previous class, right? So you could get, yes. Okay, so you have this C, right? And then, so it's not difficult to see that this integration really easily to do, right? Then you just do it, and then you will get okay. So you get the first term of the C, right, in the closed form. So suppose now next we are interested, well, in well, we're going to look at the absorption, okay? So if it happened that this two quantity are very close to each other, then before that, this, I mean, the absolute of the difference between this quantity much less than this add up together, right? This is very trivial, this condition. Then you can see that the first term is going to, I mean, the first term will be very, very large, right? Comparing with the second term, right? Right. Agree? Second term. Can you see that from the map? Are you sure? With this condition, this one is going to be very big or very huge compared with this one. Right. Then I just throw the second away. So what we have left is only the first term. Okay, so okay, I think I have to put H bar here. Sorry. Yeah, that's it. And you can apply applying trigonometric identity. Right. Then this term can be expressed in terms of the psi function. Okay. Can you see that? I just pull half of this out, right? And you will get the minus sign, half of this quantity, and you get psi. And that is the reason why you get half here. Okay? And you get factor 2 as well, because you need to divide by 2 to get the psi. All right, okay. Are we good here? Okay. Then from this we can compute probability, right? What was that? Okay. Next, can compute plot, okay, of effective of transition after time t, right, which is right. You know how to, you know that if you want to compute the plot, then you need to make a square of this c, and then you will get okay. So this is actually, I can write it. I will try to be not that kind of lazy person. Okay, so you get this out. Now we introduce a function. This Okay. Okay. This term is called energy mismatch. Okay. Mismatch. Yeah. So if you plot the graph of this function, you will see that the graph will look like, ooh, what was that? Oh. So your graph will be like, so this is epsilon, and this is your G, okay? Your graph will be centered at the origin, and it's going to give you like this. Okay, this. And this is going to give you okay. And the half width of this is roughly this one. Okay. And the height of this function is this one. So it's not difficult. If you want to compute the peak, the height of the peak of this function, you just what you need to do. What you need to do if you want to compute the peak. I mean the height of the peak of this function. How to do that in principle? Okay, let's see. If you do that, what will happen? Can you see that? I give you 5 minutes to think about this. It's just really basic stuff like yeah, from that function. No, from this function, you need to find the peak. Yeah. Well, you can do that, of course. Yeah. No, well. So, no, actually, well, you can. I will let you think about this. Well, actually, anyway, so the peak will be at epsilon equal to 0. So, well, it's something to do with the derivative, something. Okay. So this is a feature of this function, and then you may wonder why do we need this kind of function? Okay, let's see. So let's see more feature about it. If t increase, right, maximum peak also increase, right? Can you see that? The peak you get higher, yeah, because the peak, the height of the peak depend on t squared, right? Okay. Why? The delta epsilon decrease. Okay, because this you have to divide by t, right? When it when this thing get bigger, then this is get smaller, and it getting higher, right? So yeah, it's squeezed. It has been squeezed. So if we draw a graph again, suppose that this is a time t, right? And this is your graph. I think it's I'm going to put this because otherwise I don't have space to draw a thing. Epsilon. So you get peak, which is actually getting higher in this way. Okay, that's what will happen. So it means that if you look at this carefully, G will be like a delta function, right? Roughly speaking, right? In epsilon. So we can say that, so your G will be some constant times t with the delta function, which it actually depends on the epsilon, right? This is constant. And this can be determined by computing the area and the curve. Okay. All right. This C. All right. Can you read my handwriting? Curve. Sorry about this. Now, so if we try to look at this, so you do the integration of this whole thing in this way with the epsilon, right? You will get this. And so since you need to do integration with respect to the epsilon, then you can pull out C and T. Then you get C, T. And so this very obvious that you will get 1, right? And on this side, you plugged in your G function, right, which is this form. Okay. And then, so this integration is not difficult to do. So after you finish the calculation, you can find out that actually your C is 2 pi over h bar. So I left this integration for you to do at home. It's not difficult. Then, so if we take the limit at the t very large, so you get this. Well, the reason we're taking this limit, you know the reason why we have to take this limit? Yes, of course. Then this, let's make a note that actually this limit gives us the delta function behavior, right? Delta function, right? This is, you have to understand why we consider this limit of this function. So, and then we can compute and the plot. No, the plot is 2 pi h bar okay, this one. So this gives us the, if you want to draw a picture, so you can draw a picture like this. So suppose this is your EL plan, this is your ELI, right? Which is, of course, obviously, right here. So you have two level system. And it means that if you put the energy h bar omega into your system, it will be excite your system from this part up there, right? That is the picture that we have from this, right? And then this means this is a probability that once you put this energy bunch into your system will be transferred from this lower energy to a higher energy with this amount of energy, all right? No, is this amount of probability that is going to happen. Okay. Nah, sorry. Sorry. So, oops. So this is called absorption. Okay. This is called absorption process. Okay? Because your system absorbs the energy and get into the higher energy level, right? So, okay. And so actually, once you, I believe that when you learned basic quantum mechanics, you know this kind of thing happen, but there is no calculation back up, right? But now you see, really this is detailed math to actually explain this is absorption behavior, and your electron can get into the higher level of the energy in this way, okay? Next, so we're going to look at stimulated emission. So in this case, if this omega is approximately to the negative of this different energy, frequency, right? This means this condition must hold, right? Then the second term will be dominated. I mean, the second term in this CL palm. Okay. In the first case of the absorption, the first term dominates, right? And then we throw away the second term. And now, in this situation, if you set this condition, we find out that actually the second term will be dominate, and we throw out the first term. Okay, and then you get okay, and again you can rewrite this whole thing in terms of psi function, right? This is the plus side, sorry. This is also the plus side. Sorry about it. Then over 2, okay? More or less the same. You just switch the negative side for the plus side in this situation. And so you compute again the plot. A plot, okay, which is Okay, here. And next, let H1 okay. You see that the difference from the first case is that you get minus sign here, right? And then, and you also again introduce this G-palm function, which should look like more or less the same with the first one that we worked with it before. All right, which is okay. The behavior of this function is exactly the same, right? Then you know that at the t very large, so you will get more or less the delta function of it, right? That is the thing. Then p. Okay, this one. Okay, so you have this. Oh, sorry. I should be this one. And you can draw again the diagram. Okay, for this situation, you put exactly the same, a bunch of energy into your system, but what happened is that your system at the excited state will be get down, right here, and release two bunch of energy, okay, because this is, you get a minus side there, okay. This is called, stimulated emission. So normally, if not in this situation, your system will automatically get down and release only one bunch of energy, right? But in this situation, you put a bunch of energy and force it to get down, and you get two bunch, okay? Okay, so let me make a note for you. So we find that okay, you find out the probability that your system will be transferred from one energy level to another energy level will be this one, right? It depends on the process that you're looking for, right? Absorption or emission, right? Is not valid, right? It's not valid for arbitrary large t, right? Because it would sooner or later exceed 1, and this is a problem. You know that the probability cannot be greater than 1, right? But if you allow your t to be arbitrarily large, then yeah, of course, it can be greater than 1, right? Yeah. However, as we proceed all the way from the beginning, by using the perturbation technique, right? Perturbation technical method, our method, right? With condition. And okay, this is a condition that we have in mind, right? So, in short, this whole process works because we keep this constraint, right? And then we do the calculation, and then you get this kind of thing. Okay, the second point. Actually, the limit on t make no problem if we consider transmission prop per unit time. Okay, so this is called so we're going to get transition rate, right? When you divide by the time, it's going to give you a rate. So Then, so the whole business is okay. Now, it doesn't depend on time anymore, right? So it doesn't matter what kind of limit on t you consider, you will get this the rate of transition, right? Okay. Since this delta function plus is the same,
So it's constant, always constant.
yes, it's proportional to this bit, right? Yeah, yeah, yeah. That doesn't depend on time anymore. This whole thing now, yeah. Yes, of course, because we take out the time. According to the perturbation technique that we put in, and we consider the limit of that g function or that you will get the tau function, but and then you move t here, then this all will be always doesn't depend on time. You just get the constant. Yeah. But you have to keep that actually, if you look at the rate, transition rate, okay? Okay, so since this two delta function are exactly the same, then for this for this harmonic perturbation, the first order of transition rate for the stimulated emission and absorption are exactly the same, right? That is the point. Okay, so next we consider more sophisticated setup or system. This is the really a toy model, right? Then we need to get things more fun with something much more difficult. No, not that difficult, much more interesting, I would say. Okay, next. We consider continuum level. Okay. of the energy system. So it means, so far, we have this kind of two level, right? And you know how to compute this. Okay. But in most of the cases, right, there is a group of coordinate state final state with energy close to EIL, like this one. Suppose that this is your EI and this is your EL palm, then you will get something like this. You will get like a strip of energy that actually surround this EL, okay? Right. And so this is, say that EL prime plus delta E, and the lowest is minus delta E, and the width is 2 delta E. Right. Okay. So we get this kind of spectrum. Okay. That now, so what we are going to do is next is to look at this kind of system. So if we say that is the number of states in the interval then we have this, and this rho is nothing but the density of state at energy E, right? So this is my rho, so please do not confuse with something else. And then next we write the plot actually Okay, the plot, okay, that actually that go from the lowest to the highest level, then so here we replace our plum with E. Okay, so this is a discrete. This is a discrete variable to be continuous. Okay. Okay. Nothing. Okay. I just was something interesting in the back. Anyway, so so you you เอ้าจะไม่ทันเหรอ
นิดนึงครับนิดนึง
Okay. All right. Okay. I give you time. Then let's take 5-minute break. Is that okay?
โอเค
Okay.
ที่ได้พอดิสคริปต์ของเรา
Yeah. L is a discrete variable and E is a continuous one. Right. Because if you look at this, thing will be look like the continuous band. Right. That is the reason why we try to จบแล้ว Okay, so let's continue a bit, but not a bit, but a bit, yes. Yeah. Okay, so well, now we have okay. So if this is nothing but you just use this expression of this C1 that actually we compute earlier, right? And you plug it in there. And so what you're going to see that, so for the graph here, suppose this is EI. So you have, this is a graph for density of state, suppose, and you have also a graph for this G function, right? Which is going to be this one. Okay, this. So at this point, we are going to approximate that actually the curve here actually can be traced as a line, okay, if it's small enough, right. It is very small, right? Then we can treat that as just a line, a straight line. So if T is big enough, then this factor is very small, right? Right here, then delta E. Which is the width of the density of state, right here. You can compute the delta E like the half again, but this is very huge compared with this where it's very small, right? When it's getting very small, it means that the curve around this area can be approximate at the state, right? Yeah. Good. This whole bit, okay. This is the text, the text to expand that furthermore, we may treat as a constant resulting in. So if we treat this term as a constant, so you can, it means that you can pull it out, right, of the integration. So your P now become and so this term, you can do the integration, right? And by taking this as infinity, and this is plus infinity. If you do that limit, okay, so it means that this integration can be computed exactly, and then you will get pi of this. You can try it yourself, and then you get this out. Again, you have the, you see that you get t here, right? So then you can compute again the transition rate, right, per unit time. And this is known as Fermi golden rule, right? Okay, so let's have a look further. what we can what we're going to have after we have this. So next we have a look at spontaneous emission. So far we do the effect of absorption, right? Absorption and stimulated emission. Which are direct consequence of external source, right? External field. However, there is another phenomenon, right, called spontaneous emission. If you have two different energy level and your system is on the highest level of the energy, right, is have to go down to the lowest energy and then give up this bunch of energy. Sorry, this is okay. This is kind of a common process that you have learned from what happened is that is in excited state making a transition downward with a release quantum energy. Without any external perturbation. Okay, that is the reason why it's called spontaneous, right? Because it happened naturally, right? However, with the vacuum fill to make a transition. Okay? You know what is a vacuum fill, right? Yeah.
No.
And it's yeah. Well, actually, there is no fill actually, indeed, and you think that something actually invincible in that you can see that actually make this happen. That's make this transition. Actually, you can think this is like an external fill, right? But this is already there. You not need to put it to make this transition happen. It's not like the previous case that you have to put the external electric field, something like electric field to make this happen, right? But the vacuum field is already there, right? And then that makes it happen. Something like let Ni be a number of atom or electron, maybe, in the lower state, right? And NSV, a number of atoms in the upper state, right? And let S be the spontaneous emission rate. So that the number of particle or atom within the upper state by the process the unit time is this one. Yeah. Particle or atom. The stimulated emission is proportional to energy density
per unit time.
yeah, per unit time. By the process. I mean the process. I mean the spontaneous process. Suppose that you have another FB. This is the rate of the stimulated emission rate, right? Okay. So then this should be number of particles leaving upper state. Okay. Okay. And for the absorption, is proportional to then is a number of particle or atom or electron going up from the lower state. Then in total, we have the rate of change of this NF. Right. You can compute this by combine all of this. Okay. So you get a negative sign because it's decreasing, right, from the upper state. And you get a plus sign because it adds up the particle to the upper state right here. So if you draw a diagram, so you have a bunch of particles down here, right, which is an I, and you have a bunch of particles up there is EF, that we call, and F here. So once you put the external field, it means that you put the energy. This process will give you something like the particle will go up and down, and then will be release the energy out of it, right? This kind of thing. If you have the situation that the chain of the number of particles at the final state is 0, then the system is in equilibrium. Right. With the ambient field. It means that so your density of state can be expressed in this way. Okay. So it means that it's very simple algebra, because if you put this to be 0, you can solve for for the law, right? Then you get that relation. No, I forget to put AS here. It should be S here. S here. Again and again. Okay. Now using the fact that in statistical mechanics, which is I assume that you have learned something from your undergrad, but we're going to talk about this in another course after you get back from Chiang Mai. The number of particles with energy EI or energy E in thermal equilibrium at temp T is proportional to the Boltzmann factor, right? So this is a Boltzmann factor, okay? Then it's not difficult to see that the ratio, right, between the number of the particle in the lower state and the upper state, it can be expressed in this way, which is this one, right? Then your rho I here, rho E there over there, you see that they actually the ratio. Oh, I think I should put the I here. Right, sorry about that. So you can turn this into this expression. Okay. Which is, if you look it carefully, what does it look like? This kind of expression. What do you think? What does it look like? Is this familiar? It look more or less very close to the Planck radiation, right? Right. This is similar to the Planck radiation, right? Which is the Planck radiation is -1. If I get it right, then if it happens that these two factor and it should be pi square, right? H pi square c to the third, I believe. Okay, yes, that's right. If then if this had happened, it means that oh yes, indeed, sorry. Right. If this, then that one going to be nothing but the Planck radiation, right? And this term is known as the Einstein coefficient. Okay. So now, when we derive this relation, we also include the external field, right? That is the reason why. Next, if we exclude the external field, what will happen? Next, if we exclude the effect, right, of the external field, so the rate of change solely depend on this, right? And then you can solve this very easily because it just sounds very simple calculus. Yes, and then you can say that, okay. This is a constant integration of the constant of integration. Sorry. This is tau. So here tau, you can say that tau is the half-life. Half-life of the state. Okay. It means that, so this, if you plot the graph, this is T, and this is NF. So you will get the graph like exponential, like this, right? When here, it should be tau, and then this should be 3.6 something NF, right? Half of it, right? So that's it. What we have. So it means that if you have two-level system here, right here, and after that you leave the system with the tau, right, is going down, and then it's going to emit the energy bunch. So after this, you will get only half of it, right? Okay, and then the process continue, something like that, until nothing left after. Yeah, something like that. So this is what we have from, yeah, I think I stop here for today. So damn it at the moment.